All right, now we refresh a little bit what we covered previously. So you can see on your screen now, you'll be seeing a pump, cross section of the pump. You're seeing a blade. This gray color is the blade. And then you have two point of interest. One is the internal radius, which is this point and this point, or this point and this point, this point and this point. So R1 is your, we can say as your input point. Point number 2 or R2 location here is your output. And then for centrifugal pump, the water actually spraying from the middle, right? Go into the middle, and then you look at the rotation arrow. In this case, omega. Omega in this case is clockwise direction. All right, clockwise direction, so that you know that the blade is rotating according to this arrow, omega. And before you start solving a centrifugal pump question, you have to ask yourself whether you know how to draw this vector diagram or not. Okay, so vector diagram consists of U, V, and W. Okay, U, V, and W. So how do you draw the diagram? First, you identify your first point and second point, means R1 and R2 point. Then you start to draw the U. How do you draw the U? You select one point, and then you will see this one as a circle, and then you draw a tangent line. You draw a tangent line at that point, going down, right? Going down, not going up, going down, because the W is clockwise. Okay, W clockwise is going down, so your U1 is pointing down. Then the next vector you're drawing is the V1. V1 is the blade speed. So blade speed, this is the gray area, represent the blade. So blade is moving clockwise. So clockwise, the V should be pointing to the front, pointing to the front. And your W is the relative. Relative, you capture from a triangular that you draw over here. Because W, right, W is taking this shape. Okay, taking this shape. You remember there's an equation that we learned in a previous class. There's an equation of this one. V equal to W plus U. So V equal to W plus U, these two. So your W is pointing up. Okay, W is pointing up. Okay. So what I mean by vector, just recall back. So V equal to W plus U, meaning V is your resultant. So how do you draw this vector? It should be combination of vector A plus, this is C, A, B. So when you draw this vector diagram, your C equal resultant vector equal to A plus B. So you know if from this PowerPoint slides, V equal to W plus U1. So you know that W plus U1 is continuous. So you can see here, your U1, these two can be either U1 first or W1 first, doesn't matter, but it's a product. The product of these two will get V1. So if you look at this diagram, so V1, you know that this is U. This arrow must plus this arrow, so that you get the resultant of V. How you get resultant? Resultant is the starting point to end point. The arrow is pointing from starting point to end point of your vector. Starting point, end point of your vector. Okay? You do the same for the second one. And then from there, from the vector diagram, you get your alpha 1 and beta 1. Okay, alpha 1 and beta 1. Okay. How to calculate U1? How to calculate U1 given by R omega. R omega. R is the radius, omega is the rotational speed in radian per second. Okay, now today we continue to one tutorial question, how we apply what we learned in the previous lecture. Now, as you can see from the slides here, you are given a water is being pumped at the rate of 3.5 meter cube per minute. So this is in mathematic form. When at this stage, you should already know how to put this one in mathematics equation. So being pumped at the rate of 5.3 meter cube per minute. So this is volume over time, give you Q. Q equal to V times A. Okay, and recall how to get M dot. M dot equal to rho AV equal to rho Q. Okay, but this is the previous chapter. But what is important is that by reading the question itself, you should know what is this mean. What this mean. All right. Then after that, the question tell you that the centrifugal pump is operating at a speed of 1750 RPM. RPM is a revolution per minute. So you need to know how to convert RPM into radian per second. Okay, so one revolution equal to 360 degree. So 360 degree equal to 2 pi radian. So you do the conversion, RPM into radian per second. So impeller have uniform blade height, so given a B, 50 mm. With R1 is given, R2 is given. And the acid blade angle beta is given. Assume the ideal flow condition that the tangential velocity, tangential is V theta. So V theta 1 of the water entering blade is 0. So when you have the tangential velocity entering into blade is 0, it just tell you that the alpha 1 equal to 90 degree. So if this one you doesn't know what is this mean, please listen back to the previous lecture. Listens maybe one more time and you will understand what is this mean. So we also prove that when the tangential velocity equals 0, our alpha 1 is 90 degree. Okay, so this one was covered in the previous lecture. You can view back to the previous lecture video. I think the last 20 minutes before we end the lecture, we mentioned this one. So what does this question require us to do? First, we need to find the tangential velocity component at the acid, which is V0 theta 2. And then we need to find the ideal head race, Hi, and the power transfer to the float, which is W dot shaft. And then discuss the difference between ideal and actual head race. Is the power ideal or actual? Explain. So you are given a diagram that we covered previously. So you have R1, R2, 0.1 and 0.2, input and output, and I did explain how to draw the U, V, W before we come to this tutorial question. Right? Beta 2 is given, alpha 1 is given. So what else? All right, so we have all the parameter here and we can start solving this kind of question. So how do we solve? So alpha 1 90 degree, beta 23 degree, R1 given, R2 given, B is given, which is the height of the blade itself. Okay, this is your B. Rate, your Q is given, volume flow rate is given, rotation speed omega is given. However, you need to change this one to radian per second if needed. However, you can see that the Q is in minute, so maybe you don't need to change. Let's see. But normally we will change to radian per second before we start solving. And remember, the radius here is in mm. So when you do your mathematics calculation later on, remember to change to unit SI in meter, because you can see the rate is in meter cube. First, we calculate the tangential velocity component, V theta 2. So recall this diagram. Why this diagram? Because it asks us to solve at acid. Acid is point number 2. It is here. Okay, this is point number 2 at acid. So in previous lecture, we already discussed how to draw this vector form. Okay, so again, if you're not clear, go and listen back to the previous lecture. All right, so you have your U, V, and W. You have beta 2, alpha 2, and you know that your V2, you can split to V theta 2 and VR2. V theta 2 is tangential or tangent direction. Why tangent direction? Because you are drawing this vector on a circle in the tangent direction. Okay, and then why this label as R2? Because this one is in radius direction or radial direction. Okay, what mean by radial? Radial means if you have circle, this is radius. If it's along the radius direction, it means it's radial direction. Okay. Next, you use trigonometry equation. We already covered what is cot beta equal to U2 minus V tangent at point 2 or acid divided by VR2. This one also covered in the previous lecture. So you know your Q. All right, you know the Q. Q equal to 2 pi R2 B2 VR2. So this equation also covered in previous lecture. And recall how to calculate the U2. I think I mentioned this one 5 minutes ago. All right, U equal to R omega. So U2, you substitute your R2 omega, change your omega revolution per minute or round per minute into radian per second. You get your U2. Any questions so far up to this stage? If you're not sure, ask me now, because if not, I'm going to ask question later.
So far, no, sir.
Okay, good. Dinesh, you all right?
Yes, sir. So far, okay, sir.
Okay, good. Who you are here earlier? Who are you in the class?
Yeah.
Okay. All right. So the next also substitution of equation. So U VR2 given by Q, you might rearrange the Q equation into this one. So your objective is to find what is your VR2. You move this component to the left by Q divided by this one. You have your Q, you have your R2, you have your B2. Use your calculator, you press the value. What need to highlight is you need to change the minute into second, yeah? Because your V2 is in meter per second, so you need to change your Q, this one, into second. So you arrive at your radial direction of your velocity. VR2 equal to 1.58 meter per second. So basically, this is just a substitution of value. Okay. So important equation, important is that you know the diagram itself. You know how to draw this diagram. Okay. And then recall equation to calculate the beta 2 Q. So in this case, you calculate what is your U2 and VR2. Okay, the next one, once you find your R2, you find U2, you know beta 2 is given 23 degree. So basically you have this one, you have this one, you have this one. Only left out is your tangential velocity V theta 2. Substitute the value, rearrange the equation, you get what is your tangential velocity component, V theta 2. Okay, so I give you a rough idea. So your V theta 2 equal to 3 point something meter per second. All right, now roughly try to understand how we solve this kind of question, because all the value will be changed in the real scenario. All right, so at least you look at the slides, the equation seem make sense to you, then you're okay. Once you solve for A component, then we go for second component, which is the question asks us to find ideal head race, HI. So also there's an equation for ideal head race. HI equal to UV differences divided by G, U2 V2 minus U1 V1. And again, this one is tangential velocity. This one also divided by G. So as you can see, we are cancelling the V theta 1 because our alpha 1 is at 90 degree. Okay. Then you only left out HI equal to U V divided by G. You found what is your V theta 2, your U2, let's see, do we have G you have? U2, yes, just now we found your U2. So you substitute your value of your U2, you manage to find HI, which is the ideal head race. All right. Or there's another calculation you can use in a more complicated form. You can use this one, that what you see on the screen here. So you substitute, you still get the same answer, 12 meter, 12.37 meter. So for your test or final exam, please use, if can, go for 3 decimal place, right? So this one also quite direct, substitution of number. Only the catch here is here. You should know why we cancel this one. Okay, because the alpha is 90 degree. Third one, finding the power transferred to float, also standard. So we know that our float enter at 90 degree. So your power equal to T shaft omega is an important equation when you want to find power. Power equal to torque of the shaft times the rotational speed. And then there's an equation for the torque in the previous slides. So torque equal to rho Q times the RV minus RV, 0.2 minus 0.1. Okay, the differences of your RV times the omega. All right, and recall what is your U1 and U2, meaning you substitute the value of R. Okay, inside there, you got what is your U1, U2. You can either use this one or this one. Okay, same, depending on the value that you have in the question. Sometimes, but most of the time, you have your R1 and R2 and omega, all right? So in this case, again, you can cancel the U1 V theta 1 because of alpha 1 equal to 90 degree. All right, so when alpha 1 90 degree, remember your tangent velocity is 0. So something times 0, you get 0. Then the rest is the substitution. Again, just a reminder, the density, you need to refer to a table when it comes to test or final exam. There will be table given in the attached together with the question paper. So you need to refer to table. Inside the table, the loss of you need to refer to the correct value depending on the type of the fluid. You will have air table, you have water, you have oil, and other material also. So you need to refer to the correct table, correct temperature to get the density value. So in this case, we use 999. And the Q is given. Again, Q, what we are doing here is that convert the minute into second. And you have your U2, V2 just now. So U2 and V tangent at 2. So 3.7 times 32, you get the final answer. So if you do the mathematics correctly, you will get in the unit, your answer in the unit of kilogram meter square over second cube. So this one is equal to what? Okay, this one equal to what? So you can write your answer 10.708 kilowatt. Okay, so it's quite direct for this exercise. Any question before we move on? Anything you want to ask me about this tutorial question?
No, sir, no questions.
Good. Raj, any question? Raj, are you there?
Yes, sir.
You have any question, ask me.
No, sir.
No, I have question for you. What is, Raj, what is omega? What is this? Raj, what is omega?
It's a turning point, sir.
Your answer is turning point.
You want the value or what, sir?
What is omega? What is this? What do you understand about this one? What is this one? When you see omega, what does it mean? Cool. The next one I'm going to ask you. Stand by.
So speed, sir.
What speed?
What speed?
V also speed. U also speed. Omega, W also speed. What is omega? Again, remind you, you're now in a year 3 student. My question is year 1 question. Cool. What is omega? Cool. What is omega? Cool, are you there?
Yeah.
What is omega? What do you understand about omega?
RPM.
What is RPM?
Velocity.
What kind of velocity? U also velocity. V also velocity. W capital also velocity.
W velocity.
Yeah, I'm asking you what type of velocity we are referring to here.
Can I answer, sir?
Yes, go ahead. What is that?
Angular velocity, is it?
It's a angular.
Angular velocity.
Do I use angular velocity in my lecture? Shirley, you want to try to answer what is omega?
So the omega is the centrifugals, how to say the speed of turning for the centrifugal pump.
So, okay, what is the keyword I always say about omega? If you look at the diagram of this one, what does this omega tell you?
It means that the centrifugal pumps will turn clockwise directions.
Okay, all right. The answer is rotational speed. Okay. All right. Raj, what is omega? What is this omega?
Rotational speed, sir.
All right. So there's a keyword there. It's a rotational speed. Who mentioned something, but only correct 50%. You mentioned RPM outside there. The layman term outside there. They doesn't know what is RPM. You have to tell your colleague from marketing what is RPM. RPM is a rotational speed. All right. So for example, your boss asks you to buy a pump. So you try to explain why you need to buy the pump at a certain rotational speed. Your boss maybe doesn't know what is omega. So you need to explain in the layman term, right? Okay. Okay, the next one is, okay, something important here. So the actual heat race is by experiment. Okay, that's the note now. Actual heat race and meaning what is the differences between ideal case and the actual. So ideal means perfect case. All right, you can assume there is no losses inside the system. So your HI, ideal case, and actual. If you have a perfect case, your ideal value will be more than the actual one. So by meaning, say the maximum value of your actual head race, maximum will be ideal equal to ideal case. But normally you won't reach ideal case. Maximum in the heuristic, maybe you're happy if you get 80%, 0.8 of your ideal case. 80% is good enough. All right. So this is just a side note. When you go to work later on, if someone try to tell you that the actual value is higher than ideal, then you know that this salesman is telling lies to you and try to cheat you money. Okay, so this is the very important, right? Because after you graduate with a bachelor degree, we expect you to have intelligence of an engineer and not technician. All right, so you have to know, be sensitive with the numbers. Okay, next we look at the pump characteristic or pump performance. As you can see here at the lower diagram or lower diagram of your screen, right? So you have 0.1 and 0.2 and you have a pump here, right? So again, cool, this is your expert area. I'm asking about the gauge, cool. So if you look at gauge here, pressure 1 gauge and pressure 2 gauge, P1 and P2, which pressure is higher? And explain why. Cool, can you try to answer? P1 higher or P2 higher?
P1.
P1 higher.
Yeah.
How you read gauge? How you read gauge? When you pump air, what happened to the arrow? Cool. When you pump air inside, this is your gauge. What happened to the arrow? The arrow go down or go up?
Go up.
Okay, then you look at diagram. Does it logic to say pressure 1 is higher than pressure 2? Cool, you know where to look at or not? Do I need to enlarge the arrow for you?
No need.
Nah. Then which one is higher? Which one is higher?
The P2 higher, then go to P1.
No, I'm not asking you the direction. The pump will always. Do you know why do we use pump or not? We pump water, right? Okay. Now my question is that from the diagram itself, you should know how to read diagram. So from the diagram itself, P2 is higher than P1. Do you see that? Cool?
Yes.
Okay. So, and this is, we are using pump. There's a pump there. What is the function of pump? Pump is to push up the pressure. Okay, don't confuse with the normal pipe that without pump. Normal pipe, P1, P2. If P2 is higher than P1, then the flow will flow this way without pump. But now with the pump, the exit point will be higher. Take note, this is a very logic thing to say. When you go outside there, you work already, don't tell people the opposite one. You hold the title of engineer, but you tell your technician, the pressure is lower at the outside, then something wrong with your pump. Okay. All right. So if you look at the diagram, if you use pump, pressure 2 will be higher if you're using pump. Okay. And even the diagram gives you the arrow of the flow already. The arrow is going in. So arrow going out here. So the flow is going from the left to right, and you have a valve to open and close the flow of the pipe, and you have Z1 minus Z2, which is elevation of 0.1 to 0.2. This one will give you elevation differences Z2 minus Z1. And then there's a flow meter at a certain distance. Okay. All right. Now there's an equation to calculate the actual head race, actual, not ideal, actual one. So actual one given by this equation, HA equal to P2 minus P1 divided by specific weight plus Z1, Z2 minus Z1 plus the differences of velocity at point 2 square minus V1 square divided by 2G. So typically when you install pump, the elevation will be small, velocity of the head will be small, meaning the speed at point 1 and point 2 will be small, elevation will be small. Okay, what mean by elevation? It means if you have a pump, you have an input, we have an output, the distance between your input and output is actually very small compared to the overall system. Okay, the distances between point 1 and point 2 is very, very small. We talk about elevation here. Okay, so that's why you see the blue arrow canceling the equation. All right, then your actual head race will be equal to P2 minus P1 divided by omega or gamma, right? Gamma is a specific weight of the fluid. Okay, so this one also need to refer to table, this value. And one important equation that will save you in a final exam, I want to highlight this one. I put a 3-star here, means very, very important. So power transferred to fluid given by this equation, gamma Q HA. So HA you calculate. You calculate from the one of the equation. So when you okay, so this is the equation. If you express in terms of horsepower, you take the number divided by 550. Okay, if you communicate with the British or you work in the US company, they like to put their power in terms of horsepower. Then you take the calculation divided by 550. Okay. All right. Then another one is overall efficiency, which is also important formula. Overall efficiency, you take power gained by the fluid divided by shaft power. So P sub F divided by omega, capital W dot means power of the shaft. Okay. So what does it mean? I put some note on the screen here. So the lower one here is a total power applied to the shaft, or we call it brake horsepower, BHP. So this name you will see in the centrifugal pump specification. If you buy a pump, they will put a brake horsepower inside the spec there. Okay. So again, when you see 550, it means you are calculating horsepower. And if you write this overall efficiency in horsepower, you are in this form. Okay. So if a normal one, which is in Malaysia case, we don't need 550. Okay, straight away, you use omega Q HA divided by BHP. Okay, the rest you can read from my slides here. Okay, overall efficiency, you can consider hydraulic, mechanical, and volumetric dimension. So they are dot products. Hydraulic times mechanical times volumetric. So this is the typical graph that when you buy a pump inside the manual, you will see on the left hand side is the horsepower, or you will see a diagram give you HA, horsepower, and efficiency. How you read the graph depending on the line. So if you are reading the head, HA means you are looking at this line. This line is HA. Brake horsepower is this one. Okay. And efficiency is this one. This is your efficiency. So how do you read from this graph? Once you know your flow rate Q, for example, if your Q value is at here, what you need to do is just project. You use a ruler, draw a dashed line like what you see on the screen here, and then you can read your head, horsepower, and efficiency. So this point, you project to the left, you get one value for brake power. Here, to read the head value, you read to the left, you get one value here. And to get the efficiency, this is the maximum or design efficiency. It is give you the maximum value of your efficiency. Okay, so by practical, what is inside this graph, what is the most important to do your job, right? Most important line between these three lines, H, efficiency, and brake horsepower, is the efficiency line, because we want to get the optimum efficiency. Okay, so take note, when you purchase pump, the first line you look at the handbook or specification graph, HA horsepower and efficiency versus flow rate. The first line you look at is efficiency. So you go to efficiency, go to the peak of the line. Go to the peak of the line, see what is the value of the pump. So for example, 0 to 1, you know that efficiency maximum is 100%, which is 1. So in this case, I will assume you'll get around 0.8 something. Okay, 0.8 means 80% efficiency for this pump. And then at the maximum performance of this pump, you project down, you get a value of your Q for your system. Meaning, if you're using this graph, the maximum, let's say this graph is for this pump, the maximum Q that you can generate from this pump, you read from this graph, your Q value is here. Sorry, your Q value at the end of the pump input and output, your Q value at the output is this value. Okay, Okay, just to recap. Dinesh, are you there?
Yes, sir.
Okay, by looking at this graph, head line, efficiency line, brake horsepower line, which line is the most important line?
The brake efficiency line.
Again, repeat your answer.
The brake efficiency line.
The
Brake efficiency line.
brake, this line or this line? Just now you mentioned brake efficiency, but on my screen here, I'm seeing brake power line, efficiency and head. There is no brake efficiency line. So which line you are referring to?
Efficiency is the center one.
Efficiency line, huh?
Yeah.
Okay, correct. So you're looking at the optimum value there. This is the most important line on the graph. Okay, then it will give you three value that is related. Once you get the efficiency, you get your Q, you get the brake horsepower value, you get the maximum head value or the optimum head value when you operate at this efficiency. Okay, so again, the sequence, you look at the efficiency, then from the efficiency, you draw a line down, you get 3 points. 1 point is for head, 1 point is for head horsepower, 1 point is for volume flow rate or flow rate Q. All right. Another chart that you will see in the pump handbook, you are seeing this chart giving you a few axes. On the left, you see head. Below is your Q, gallon per minute. This one is in imperial, right? I apologize, I'm not having the unit SI so far. All right. I'm only having a imperial unit sample. And then on the right hand side is the NPSH in feet. So later we will look at what is NPSH. Okay. So this is another graph that you should be familiar after this. So this graph, these two graphs is important when it comes to selection of pump. Okay, selection of pump. So maybe after this, some quality control officer from the education ministry, they will send someone to check on your learning outcome. So they will ask a simple question, for example, in the fluid mechanics 3179, did the lecturer teach you how to select pump? Right? So your answer, standard answer is yes. Then the next question they will ask you is, can you elaborate how you select a pump? Right, in one sentence. So the answer is by referring to a graph. So a graph you can refer to is these two graphs. One is the head brake efficiency versus Q graph, and another one is a head capacity and NPSH graph. These two graphs will help you to decide whether you are selecting the correct pump for your operation or not. Okay. All right. So we're going to look at what is NPSH now. NPSH. So as you can see, pump, a question I asked Ku just now. When you're having a pump, P1 always higher or lower? Ku, when you're using pump, P1, P2. P1 is lower or higher?
P1 low, then P2 high.
Correct. So as you can see from the screen here, lower pressure always happen at suction side, which is on the P1. And then there's one phenomena called cavitation. Cavitation is something that we don't want to see inside our system. Cavitation is small bubble inside the system, because you know that when you generate energy to the fluid itself, if you are using pump, you will see bubble inside the system. This is not what we want, because this one, cavitation, or this small bubble, it will create a water hammer. Okay, it will create a water hammer phenomena, and also it will damage the pump, right? So cavitation is another word, is important in turbo machine. All right, cavitation is a small bubble inside the pipe or inside the water. Okay. Okay, so this one is what happened, right? So this is a phenomena. The pressure will be a bit lower, right? And cavitation will cause efficiency loss. Given by this equation, NPSH given by PS divided by omega. What is S? Is static pressure. Vs is the velocity, static velocity, divided 2g plus Z minus PV divided by omega. This is the vapor pressure. This one referring to table. Each property, each material on this earth will have their own property. One of the property is vapor pressure. Okay. So the first one is the differences between the suction set, the inlet and outlet, right? Z, you know, usually 0. And this is the liquid vapor pressure at the head. Later, we look at one example, how we apply this equation. All right. So as you can see, there's a diagram to calculate NPSH later on. Okay, so just as a theory, you have two value of NPSH of our interest. One is required, one is available. One is required, one is available. Denote by one is R, one is A. Okay, now by looking at the word, what does it mean? It means what is needed. All right, what is available? So for example, this is your wallet and you want to buy a balloon. Okay, balloon costs 5 ringgit. In your wallet, you have 10 ringgit. Meaning the pump can work. Okay, so what happened if you want to buy something? Let's say you want to buy a phone, right, or tablets that cost you maybe 2,000 ringgit, but your wallet only have 1,000 ringgit. What is available is less than required, then the system doesn't work. Okay, this is a general idea. What is, we look at the detail of the equation later on. We'll go for a short break. Then we look at what is required, what is available. At here, you get the concept correct first. Required is what is needed. Available is what you need to supply or you can supply. Okay, so the value must available must more than required so that the system can work. All right, we have a short break. Let me stop the recording.